switched to a dummy, or of course I can switch it back here to a speaker, alright? And that means I can use what I need to use, speaker or dummy, so it always depends, but you also can do it here, so you can disconnect here your dummy resistor, and instead you connect a little speaker to here your test lead, and that's it basically, right? And on the other jack here, my output jack, so that is what I already told you. It is again exactly what we have here in parallel. I pick here my signal, so that is the whole secret, so really nothing special. Okay, as we already heard, there is hum still, and now when I told you this is noise, let's see how this looks like on a spectrum, on an audio spectrum analyzer, to see or understand a little bit better what I mean. Okay, so I've just here unplugged the radio, so here our input is open, so we do not have a signal present at our lab monitor, and now let's go over to our spectrum picture, that we can talk a little bit about that. Okay, and here it is, and as we all know, a spectrum analyzer is a very, very sensitive instrument, so you always see spikes and what have we, because you know, a spectrum analyzer is able to listen to fleas, you know, and therefore you see here all the movement. Okay, now I connect the radio back here to my little lab monitor, and you see our audio is turned completely counterclockwise, so we have here minus 100 dB full scale, and you see it is more or less flat, but as I said, there is no audio on for the moment in time, right? Now I increase the audio, and you will hear it, of course, in the speaker, and suddenly you see and you hear that our red line, and now I switch it to dummy, that we do not hear this annoying audio, and yeah, as I explained, now we are testing in parallel at the 8 ohm dummy resistor, yeah? And what we see here is that our noise level is getting up, right? So we hear noise, and as I already discussed, and as we already discussed before, it sounds a little bit funny because there is hum in the background, and here on the spectrum we already see that at 100 Hertz we have here a spike, and that is a distortion, and that is what we clearly can hear in the audio, and I can tell you what it is. It is my LED light is doing this. So that is a cheap Chinese LED light, and it is producing a distortion, and you clearly see it and you hear it. And for instance, if I go now over to the light switch, and when I switch it off, have a look. Now the distortion is gone. I switch it back on, see all the spikes are coming back. So that is a very, very bad LED light, producing really a lot of noise and heavy distortion. So if you have LED light like this close to your Radio Shack, right, you always have this distortion, and this distortion is able to really eliminate your signal you want to hear on the radio. So all these LED lights are very critical. Anyways, now we really have here only noise, okay? And of course I can change the level here on our spectrum analyzer by simply changing the volume. So now, don't know if you hear it in the background. It is not very strong. Now I increase here my audio, and while I increase my audio, you see it is coming up, and you see a second point or a second issue. You see that suddenly here at 5 kilohertz our signal is going down. So here we have 5 kilohertz, and you see here over, I don't know, here from 100 hertz or from 200 hertz, whatever, up to 3 kilohertz, it is more or less flat, and then suddenly you see that the noise level is going down. And that is simply because I have the CCITT filter in. So the CCITT filter is something we have, of course, present at our Rohde and Schwarz radio communication tester. It is present at the CMT and as well on the CMS. So on both I'm able to switch in the CCITT filter, and that makes the audio more in a range where you normally hear a voice, right? So we do not need the very high frequencies, so the CCITT filter just reduces this area, which you definitely do not need for receiving a radio signal, and therefore you can prepare your tester to only display the range where you normally hear a radio on receive. So that is sometimes very helpful, because for instance you see here little spikes. I mean, this little spikes here at what is it, 15, 17 kilohertz, so these are not very strong, so you wouldn't hear it. But on the other hand, there could be, for any reason, spikes which are more dominant, and therefore it is nice to have a filter like we have it here, to be able to reduce those distortions. On the other hand, radios, I mean our communication sets, our shortwave radios, are normally having an internal filter as well. So normally you are not able to have a very strong audio signal at 10 or 20 kilohertz. So your internal filter in your shortwave radio is normally reducing these parts of the audio signal as well. So the CCITT filter is only an addition to what you already have in your radio. Okay, so again, what you see here is noise. But coming back to what we discussed before, we just want to understand this signal-to-noise ratio, okay? And why can we use it as indication? And therefore, it is helpful to see it first on spectral analysis to have a idea what's really going on. Okay, so the next step is I have now connected my signal generator to the radio, and you might have seen that the radio is adjusted to 14.1 megahertz delay with 12 meter band, and for the multi-time I'm not putting out any power to the radio, and that is the reason why we still, and you can hear it, we still have only noise, so there is definitely no signal. Okay, now I leave here the speaker on, and I switch my generator, and the radio is set to AM. So additional to that, I use 35% modulated AM signal, and always when we are testing, we are using, not always, but most of the time, we are using 1 kilohertz P02.5, and that is what I've adjusted here, 30% modulation, and 1 kilohertz. switch it here to dummy. It is easier for us. A signal which is still very, very much in the noise is very difficult to understand. So what we really would like to have is a signal which is strong enough to be able to overcome our noise level, so that the distance, if you will, between the noise and our audio level is that huge that we only hear the tone. And let me tell you that what we have here, so once again, all the noise in the background with only our little signal here is a minus 115 dBm signal. So that is really a very low or very weak signal which the radio is able to pick, but the voice wouldn't be easy to understand. So that would be, I don't know, a radio 3 or radio 4, radio 3 or radio 2 signal maybe, but definitely no radio 5 signal, which is the qualification on the audio signal. If you're giving somebody on your radio a 5.9, so that means 5 is standing for a very clear audio, and 9 is a signal which you're reading on your S meter. And always when you tell somebody on the radio, yeah, your signal is 5.9, that means that you really have a very clear audio, okay? And in this case here, that may be radio 3, I don't know. So that is not very good. It becomes harder and harder to understand. But now we are going back here to speaker, that you can see our signal, that you can see our noise. And now let me increase here my signal and watch here our 1 kilohertz and listen to the tone. It's getting louder and louder, and what you see, our signal is getting stronger and stronger. Okay, so now we are at minus 90 dBm and almost no noise in the background. And you may remember minus 73 is an S9 signal on the radio. Now we are at minus 80, and I go straight to minus 73. I know the tone is annoying, but we need it to get the difference. And now, if you listen to the tone, there is no noise anymore in the background. I switch off the speaker because it's really annoying. We are back on dummy, but we have the same here on our screen. What is the difference? The difference is this is a minus 73 dBm signal, so that means it is S9, okay? And now you see, if somebody is producing an S9 level, normally this station would get over with radio 5, because with an S9 high frequency level, the audio should be able to get out of the signal with a very good quality, and that is definitely what we can hear here. So it is more or less it is VHF quality, if you will. Right? So, and you see it here as well. So, if this here is our noise, or not if it is a noise, you see that now 1, 2, 3, 4, 5, 6. So, there is a difference of 60 dB here, so minimum here for our tester here, and that is now the difference between the noise level and the signal. But on the other hand, what you can see here as well is that you see this here, and what you see here are harmonics of our 1 kilohertz tone, and so this is total harmonic distortion what you can see here. So this is always getting into the final signal, if you like, and therefore if you have here a very high total harmonic distortion level, that means that the sine which we would like to reproduce at pure sine could be distorted by maybe a bad